Right. Last time we finished Bohr's model. Last was the limitations of Bohr's model. Now, on the basis of Bohr's model, we'll derive Rydberg formula. If you remember, I told you Rydberg formula, that is 1 by lambda is equal to 109677 into z square multiplied by 1 by n1 square minus 1 by n2 square. That was to calculate wavelength or wave number of radiation emitted or line emitted. Its derivation is a part of your syllabus, but it's not frequently asked. See, if you remember, I told you that during a spectrum of hydrogen, electrons absorb energy, go to higher shell. There they become unstable, and to stabilize themselves, they lose energy in the form of radiation, and they come back to a lower energy level. So when the electron jumps from a higher energy level to the lower energy level, what is the wavelength of radiation emitted? That will depend on from which shell it comes to which shell it goes. That will depend on these two shell numbers. So how do we derive it? This is on the basis of Bohr's model. Now, in this case, will you be using one point of Bohr's model? If you remember, I told you that energy, according to Bohr's model, energy of electron in any shell is equal to minus 2.18 into 10 to the power minus 18 joules per atom. So this formula will be using in the derivation of Rydberg's formula. Right on. During line spectrum of hydrogen, electron from a higher shell within brackets N2, electron from a higher shell within brackets N2 comes to lower shell within brackets N1, and during the process it loses energy in the form of radiation. Loses energy in the form of radiation. This energy released is given as follows. So we are calculating energy and then we'll convert into wavelength. So you have to just copy the derivation. Delta E, En2 minus En1. Delta E means change in energy, and that will be energy of electron in shell number 2 minus energy of electron in shell number 1. Now, energy of electron in shell number 2, N2 and N1 will be using Bohr's formula minus 2.18 into 10 to the power minus 18 into Z square divided by shell number is N2, N2 square minus, for this one, minus 2.18 into 10 to the power minus 18 into Z square divided by N1 square. Now we'll take 2.18 into 10 to the power minus 18 will be common. 2.18 into 10 to the power minus 18 into Z square. This is common. Within brackets. Now this minus becomes plus. So minus 1 by N1 square minus 1 by N2 square. According to formula, units will be joules per atom. Now, energy or energy difference is one and the same thing. If I say that energy, that is E is equal to hc by lambda, it means I can say energy difference is also hc by lambda. So I can say this is hc by lambda. Now 1 by lambda, which is nothing but wave number, will be 2.18 into 10 to the power minus 18 into z square. This part I'll use later, divided by h and c. Value of h 6.6 into 10 to the power minus 34. If you use units, then it will be joule second. Joule second. Velocity of light 3 into 10 to the power 8. Now we'll use in centimeters. 10 to the power 10 centimeter per second. This z square, I've substituted values of h and c. Now remaining part will be one thing more. Here units are joules per atom multiplied by 1 by n1 square minus 1, sorry, 1 by n2 square. Now, if you multiply, divide this part, if you multiply and divide this, this will come out to 109677. That is, this will give the value of Rydberg constant into z square multiplied by 1 by n1 square minus 1 by n2 square. And if it work out units, it will be centimeter inverse per atom. Centimeter inverse per atom. And this formula is, Rydberg's formula. Now listen. In the spectrum of hydrogen, some line is very bright, some lines are dull. If the line is bright or the line is dull, why it is so? See, during the experiment in the tube, we take many countless number of hydrogen atoms. If electron in 100 atom jumps from shell number 3 to 1, there will be some intensity of that light, some brightness of light. In place of 100, if if the same transition from third shell to first shell takes place in 1000 atoms, then line will be same because wavelength will be same, but brightness of light, brightness of line will be more. It means I can say more the number of atoms in which a particular transition takes place, more will be the brightness of line in the spectrum. Right? Right on this part. Each line, right? Wavelength will not change. Each line in the spectrum corresponds to a particular transition, and therefore a particular wavelength. More the number of hydrogen atoms in which electron undergoes same transition more will be the number of photons of same wavelength emitted, and thus more will be the brightness or intensity, brightness or intensity of a particular line in the spectrum, particular line in the spectrum. Now we are coming to next two small but very important topics. If you remember, last time I told you limitations of Bohr's model. Last two limitations were Bohr's model could not explain dual nature of matter. Bohr's model could not explain Heisenberg uncertainty principle. Now, these are the two next topics which we are going to take up. These are small but very important topics. Heading is dual nature of matter. Dual nature of matter. See, if you remember, we studied the topic dual nature of radiation. That is, radiation has wave nature as well as particle nature. Although for a layman, it's difficult to believe that radiation has particle nature as well. Because I'm standing under this tube light, there are countless number of photons emitted and they are hitting my body. But I don't feel anything. We walk in the sun, we stand or sit in the sun. There are millions of countless number of photons which hit our body, but we don't feel anything that something is hitting us, right? But we believe on the basis of experiments. That is which experiment? On the basis of I told you wave nature was confirmed on the basis of diffraction and interference, right? So and particle nature was confirmed on the basis of scintillation experiment, those spots which were produced. So since we can believe, we experimentally believe that radiation has not only wave nature, has particle nature as well, then later scientists thought that if we are ready to believe particle nature of radiation, then why not a particle in nature in motion? Particle in motion is naturally a particle. Why not a particle in motion should also be associated with a wave nature? But the problem is, if we see any particle in motion, first of all, let me clarify, particle in motion here does not mean a particle which is moving on a stationary surface. Here, particle in motion means particle in flight. Dust particle is flying, cricket ball is flying, aeroplane is flying, planets are moving in the um, they're not moving on road, they are flying. These are flying objects. So particle in motion means particles in flight. So any particle in flight we see, like aeroplane or cricket ball, we do not see it traveling like a wave. But there was a scientist called de-Broglie. He derived an equation to calculate wavelength associated with a particle in motion. He confirmed that particles in motion are associated with wave nature as well. But why do we not see any particle moving like a wave? That will be clear from the relation from the equation which I give you in this topic. Right on. Scientist was de-Broglie. Right on. De-Broglie pointed out that if radiation has wave as well as particle nature, wave as well as particle nature, comma, matter in motion, matter in motion, within brackets write down in flight. Motion means flight here. Matter in motion should also have the same type of dual nature. That is, a particle in motion should be associated with wave nature as well. Associated with wave nature as well. Wavelength associated with a particle in motion can be calculated by using the following de-Broglie equation. Equation is named after de-Broglie only. De-Broglie equation. Note down, it's a very simple equation. Lambda is equal to h by p. P is momentum, or I can say h divided by mv. Lambda is the wavelength associated with the particle in motion. This will be in meters. H, you know the value and units of H. I need not repeat that. M is the mass of the particle in motion, which will be taken in kilograms. V is the velocity of the particle in motion, and that will be in meters per second. See, first of all, it should be clear in your mind that de-Broglie equation is applicable to particles in flight. Motion means flight. Number two, this equation is applicable to any particle in motion, any particle in flight, right from planets to dust particle to electron, proton, any particle in motion. But if you look at this equation carefully, then you will realize, why do we not see an aeroplane moving like a wave? Why do we not see a cricket ball moving like a wave? Even dust particle, if you make a video and see it in a slow motion, it will not be visible traveling like a wave. Then why did I say de-Broglie equation is applicable to every particle in motion? Look here. Wavelength associated with the particle will be inversely proportional to mass of the particle and velocity of the particle. Remember, even a dust particle is a heavy particle for this equation. I'll repeat, even a dust particle is a heavy particle for this equation. So as mass increases, velocity of the particle increases, wavelength associated with the particle decreases. And since I said dust particle is a heavy particle, then forget about cricket ball or a planet or any other body like aeroplane moving in motion. They are much heavier particle. Wavelength associated with them will be negligible, and this is the reason we do not see them traveling like a wave. Apparently, we do not see them traveling like a wave, but remember, they are traveling like they are moving like a wave. Wavelength is very small. That is why we are not able to feel or see as if it is moving like this in the form of wave, right? But equation is applicable to every particle in motion. And if we consider a very light particle like electron, proton, or a single atom in motion, they are very light particles. And for such light particles, wavelength will be very significant. and they really seem to travel like a wave if you view them under an electron microscope, a very powerful microscope called electron microscope. They really seem to travel like waves. Now write down. I've explained so much. Write down. According to this equation, wavelength associated with a particle in motion decreases with increase in mass and velocity of the particle. That is why macroscopic, not micro, macro, big particles. That is why macroscopic particles like an aeroplane, a cricket ball, a dust particle, etc., are associated with such a small wavelength that they do not seem to travel like a wave. Next paragraph. Later, dual nature of electrons and particles in general was confirmed. Wave nature was confirmed on the basis of diffraction and interference, while particle nature, although they are particles, but still if you want to prove, but while particle nature was proved on the basis of scintillation, SCINTILLATION, on the basis of scintillation experiment. Now, what are these scintillations? See, if we take a zinc sulfide screen and if any particle hits it, it will produce a small spot or it will produce a glow. This spot or the glow produced on zinc sulfide screen, this is called scintillation. And these scintillations are produced only by particles when they strike zinc sulfide screen. So continue writing in the same paragraph, confirmed on the basis of scintillation experiment. Full stop. Scintillations are small spots produced on zinc sulfide, ZnS coating when a particle strikes it. Electron microscope, this is a very important application which I'm giving you. Electron microscope is based on wave nature of electrons. of electrons. Check your WhatsApp. I've shared one numerical, we'll solve it. Numerical is calculate wavelength associated with a molecule of mass so many grams moving with a velocity of 720 kilometers per hour. Still, we'll be using de-Broglie equation to calculate wavelength. And for that equation, we need mass in kilograms. Gram into kilogram is easy, that we can do. But we need velocity of the particle in meters per second. In this numerical, we are given 720 kilometers per hour. We'll have to convert this velocity into meters per second. And how do we convert? Multiply by 5 and divide by 18. So velocity in meters per second will be 720 into 5 by 18. This will come out to 200 meters per second. Now, lambda is equal to h divided by mv. H is 6.6 into 10 to the power minus 34. Mass of the particle is 6.62. We can take 6.625. Mass of the particle 6.625 into 10 to the power minus 22. This is the mass in grams. Further divide by 1000. That is into 10 to the power minus 3. This is the mass of the particle in kilograms. And divided by velocity in meters per second, 200. This will come out to 5 into 10 to the power minus 12. Answer will be 5 into 10 to the power minus 12 meter. See, practically, if you think, we do not see any particle in motion which is moving like a wave. And if you're not able to see any particle in our daily life, I'm saying, if you're not able to see any particle moving like a wave, it means we can say this de-Broglie equation has no importance, no significance for a common man, because in his daily life, he does not come across this type of situation. It's only scientists dealing with very light particles like electron, proton, that they are able to see such light particles moving like a wave. So sometimes the question comes, what is the significance of de-Broglie equation? Right on. This is the next topic, and it's just one sentence. Heading is significance of de-Broglie equation. Significance of de-Broglie equation. It has no significance. It has no significance, that is importance, in our daily life, because we do not deal with small particles like electron, proton, neutron, etc., for which the value of wavelength is significant. Right? So we do not deal with this type of particles. And then type of particles which we deal with, type of particles which we daily see are heavy particles. For them, wavelength is associated, but wavelength is very small. We do not observe them as if they are traveling like a wave. Next topic. Again, a simple topic, a small topic like this one only. Heisenberg. I'll write the spelling. Heisenberg. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. See, if you want to find out two values of two parameters, number one, accurately without any error. Number two, simultaneously means at the same time. What are these? Position and velocity. So if I want to find out exact position and exact velocity of a particle in motion, listen very carefully, because the definition will include everything which I'm explaining now. So if I want to determine their position accurately, I can do that provided they are to be determined one at a time, or they are to be determined together but for a heavy particle in motion, big particle in motion. But if it is a light particle, remember when I say light particle, even dust particle is not a light particle. Particle like electron I'm talking about. So if I want to find out the exact position and exact velocity of a light particle like electron in motion, I can determine their exact value at different time intervals. That is, I can determine one at a time without any error. But if I have to find out their values at the same moment, that is simultaneously, then it is impossible. That's what is the definition of Heisenberg uncertainty principle. Now the question comes, why can't we determine exact position and exact velocity of a light particle in motion, and that too simultaneously? For that, I'll give you the reason later. First, we take up the definition, mathematical expression, then we'll come to the reason. Right now, it states that, remember, missing out any word in this statement means meaning of the statement will completely change. Okay, it states that it is impossible to simultaneously and accurately determine the position and velocity of a subatomic particle. It's mentioned subatomic means smaller than atom. Subatomic particle in motion. I'll quickly repeat it in case you have not been able to write completely. So it says that it's impossible to simultaneously and accurately determine the exact position and velocity of a subatomic particle, like electron, of course, in motion. Mathematically, I'm giving the formula. Mathematically, delta x into delta p is equal to or more than h by 4 pi. What's the meaning? I'll tell you. Delta x into p is momentum. Momentum is mv. When the particle moves, its velocity may change. Its velocity determination in the velocity may be an error, but we can determine exact mass of the particle even when the particle is stationary. So m will be constant into delta V will always calculate minimum value. That is why I've taken equal to h by 4 pi. Or I can say delta x into delta V is equal to h by 4 pi m. Now we'll label it. Delta x. Delta x is uncertainty. Remember, uncertainty is nothing but error, right? Uncertainty in position means when we determine position of the particle in motion, how much is the error in its determination? That is delta x. Within brackets, its units will be meters. Delta V. This is uncertainty. Again, uncertainty means error. Uncertainty in velocity. Within brackets, its units will be meters per second. On the right hand side, h, 4 and pi are constants. You know, m is mass of the particle in motion, which will be in kilograms. In kilograms. Now, listen carefully. For particular particle, naturally we can find out the exact mass of the particle even before it starts moving. Right hand side is constant. H, 4, pi and m all are constant. If right hand side is constant, it means product means multiplication. Product of these two errors, product of these two uncertainties is also constant. What does it mean? It means if one error increases, the other error will decrease. It's something like this. If you take a balloon, fill with air and tie it. If you press it from this side, it will swell up from this side. If you press from this side, it will swell up from this side. Because total volume of air inside the balloon is fixed. Air is neither entering nor coming out. Similarly, product of uncertainties of two values, that will be constant. If we determine one value more and more accurately means lesser and lesser error. So if we determine one value more and more accurately, then error in the other value will increase. First you write this much, then what is the reason? I'll explain and dictate you. This equation shows that if the position is determined, almost accurately, not accurately, right? When I say almost accurately means minimum error is determined almost accurately. That is, if delta x is very small, then uncertainty in velocity, that is delta v, will be very high, and vice versa. Next heading, right on. Explanation of HUP. Heisenberg uncertainty principle, I'm saying HUP. So what is the explanation? That we increase the, if one error decreases, the other increases. What is the explanation for that? First, try to understand. I'm explaining. I'll dictate later. See, if we want to see any particle, if we want to find the velocity or position of any particle in motion, we'll have to see it. And how do we see any particle? If this is a piece of chalk, how do I see it? Light falls on the surface of this piece of chalk. It's reflected and then enters my eyes. Light falls, reflected, enters my eye. Then only I'm able to see this particle. So let us say this is the particle in motion whose velocity and position I want to determine. For that, I'll have to see it. And to see it, let us say radiation of wavelength lambda falls on its surface. Radiation of wavelength lambda falls on the surface of this particle whose position and velocity I want to determine. Now, there is a law called law of optics, and that law says that when we determine the position of any particle, when we see and determine the position of any particle, minimum error in the determination of position will be equal to the wavelength of radiation used to see that particle. It means if this is the exact position of particle, I'll not be able to see this particle at its exact position. Rather, I'll be able to see it either lambda to the right or lambda to the left. So minimum error will be equal to wavelength of the radiation used to see that particle. Now, how can I minimize this error in locating position? For that, I can use radiation of low wavelength. If I use radiation of low wavelength, this error will be minimized. But there will be another problem. And that problem is E is equal to hc by lambda. If I want to minimize this error, I'll have to use radiation of low wavelength. If wavelength of radiation is low, then energy of photons will be high. And if a high energy photon strikes this particle, high amount of energy will be transferred to it, like Steiger transfers its energy to the coin when we play carom. More the energy of Steiger, more is the energy transferred to the coin. So I repeat, to minimize this error, we can use radiation of low wavelength. Wavelength is small means energy of photon is high. If energy of photon is high means high amount of energy will be transferred to the particle in motion. And if high energy is transferred to the particle in motion, it means its velocity will drastically increase. And if its velocity drastically increases, naturally will not be able to determine its exact velocity. So if I want to minimize this error in velocity will be very, very high, naturally, and vice versa. So if we reduce error in one, error in the other value will increase. Right on. Heading you have written explanation of HUP. Right on. Say radiation of wavelength lambda is used to see the electron, and determine its position. According to the law of optics, position determined will have a minimum inaccuracy equal to the wavelength of radiation used. To minimize this error, we can use a radiation of low wavelength, but according to, write this equation, but according to E is equal to hc by lambda, photons of low wavelength will have high energy. If a high energy photon strikes an electron, velocity of electron will drastically increase. That is, the value of delta V will increase. Delta V will increase. I've shared one numerical based on this topic. Earlier, it was de-Broglie equation, numerical number 10. This one is numerical number 11. Calculate uncertainty in velocity. That is, we have to calculate the value of delta V of a particle of mass 10⁻⁻12 milligram, whose position is known to an accuracy of plus minus 10 picometers. Plus minus means uncertainty, this way or that way. So we'll not take 100 plus 100, 200. We'll take one side, that is 100. So value of delta X is 100. Delta V we have to calculate. So this is delta X into delta V is equal to H. H, you can take 6.6 or you can take exact value 6.625 to 10⁻⁻34 divided by mv. Mass of the particle is given 10⁻⁻12 milligram, but we have to convert into kilograms. So 10⁻⁻12 into 10⁻⁻6. So dividing by 1 million will convert into kilograms. So delta X into delta V is equal to H by M, H by 4 pi M. This is M, now 4 pi. 4 and pi will be 3 point, it's better to write 22 and 7. Divided by 22, numerator is 7. So when you calculate, this will come out to, as given in the answer, 5.27 into 10⁻⁻7 meter per second. Now to wind up this topic, again, a very, very small topic of one sentence. Write down significance of HUP. Significance, importance of HUP. Remember, again, there is no importance, there's no significance of HUP in our daily life. The reason is again the same, because we do not deal with small particles like electron, proton in motion, for which uncertainty values will be large. So many photons are hitting me, but it's not that my velocity is increasing. I'm traveling, I'm moving at the same speed. So it's only light particles which are affected. So write down significance of HUP. It has no significance in our daily life because we do not deal with small particles like electrons, protons, etc., for which values of delta x and delta v are large, right? So no significance that way.